So today we are continuing with quantum model, which is part of atomic theory, okay? And atomic theory is a nice time for us to stop for a minute and talk about something called the nature of science and its relationship to knowledge, because we're now in week 3, right? We've been at it for 3 weeks now. We've talked about the scientific method, right? We talked about the process of science. And I told you that as the semester goes on, right, we're going to see how the relationship between what we know from data and our theories changes, right? We talked about several examples of that. So now is a good time, since we're at it, we've been at it for 3 weeks, let's stop and talk about the nature of science. Just talk about science for a few minutes. The science as an enterprise. Oh gosh, right on. Okay, so the scientific method, what we call, right, it follows a procedure. Right? You begin with some sort of observation or some sort of experiment, some sort of data, right? You begin with that. Remember, we talked about this in the first day. You begin with some sort of observation, right? And then what do you use to interpret that data? Well, you can't just go straight from observations to conclusions, right? You have to use something to interpret your data. You know, if I hand my 2-year-old some data and say, here, come to a conclusion, he's missing a piece. What piece is my 2-year-old missing? He's missing the theory part or the model part. Even my 4-year-olds for some stuff, right? They can classify solids and liquids and gases. But even that's applying a theory to an observation, right? There's a big piece of the puzzle here. You take your observation and you apply some existing theory that you already know to that observation to come to a conclusion, right? My 2-year-old can't do this because he doesn't have any knowledge of the theories and the models yet. He's working on learning them, right? I mean, a 3-month-old understands gravity, but he doesn't understand the concept, the theory of gravity, right? The 2-year-old is at the observation stage and can come to some sort of conclusion, but it's not a real rational conclusion. He's missing this piece, right? And so if we modify the theory, we'll get a different conclusion based on the same data, right? The same data will lead us to a different conclusion if we modify this piece. And so far over the semester, we've seen that happen twice, right? We saw that happen with phlogiston theory. We also saw that happen with atomic theory, right? We saw the movement from phlogiston theory to what we now know as burning. And we've talked about several models of the atom, right? Thomson model and quantum model are not the same thing, right? And there's a big gap between getting from Thomson to quantum. So with the phlogiston theory, right, there was the observation. We observed, I say we as if I was there. Scientists, people observed burning decreases the size of an object, right? You burn something, it gets smaller. And so the theory was phlogiston theory, right? That was the lens that you were looking through. And so in terms of the lens of phlogiston theory said burning releases phlogiston, right? That was how these data were interpreted by that theory, by the theory of phlogiston. Okay, well, what about Lavoisier's work? Same observation, burning decreases the size of an object, right? What's the conclusion that Lavoisier came up with? Well, it's not phlogiston, right? It's a chemical change that's producing gases, and those gases are not usually trapped and measured, right? If you're burning something in your chimney, the gases are going up. You're not capturing the gas, therefore you're not seeing its mass, right? You have this big giant log and that looks smaller. Well, that made gas, that went away. That was looking through the lens of conservation of mass, right? That was what Lavoisier's work was. Notice it was the same observation. Burning decreases the size, burning decreases the size. Different lens gave different outcome of the same data. Do you see where I'm going with this, right? So, the scientific enterprise, this is what we call the scientific method, right? And these conclusions are leading us to continue testing our theory and our model, right? And so for the changes we've seen to atomic theory, what would this picture look like? We first had Thomson's model as the lens we were looking through, like the glasses, right? That was the lens that we were looking through to come up with a model of the atom. And that model was used to explain data. And then that model wasn't quite working to explain data anymore, right? That's why testing was done for Rutherford's model, right? And then Rutherford's model really wasn't great at explaining data anymore. And so then there was Bohr's model, right? And then Bohr's model wasn't really all that great at explaining observations anymore. So then now there's the quantum model, right? Every time we change the theory, we're changing the way we interpret our data. We're putting on a different pair of glasses, right? So now it's time to be challenged. We're gonna think a little bit. Whew, you ready? Okay, which piece here is required for this model to work? So in other words, of these three things, which one, if I took out, would just make the whole thing implode? I mean, assuming that we're not gonna stop observing, right? Because if you stop observing, you're dead. So if you're dead, you don't care, right? Assuming you don't stop observing, what's the linchpin for the whole thing? Which piece does my 2-year-old not have, right? It's the theory, yes? The theory is what's changing. And I've presented 2 examples of theories that have changed over time and how those theories have changed the way we interpret those observations, those experiments, those data, right? But here's a problem, and this is a problem that every scientist is gonna have to deal with. And this is something that every good scientist should think about at some point in their educational career. So science is all about measuring things, right? That's what we like. We like mass and volume and temperature, density, all that great stuff. We like numbers. But here's the real problem that scientists have to grapple with. Can we measure the knowledge that was used to make those theories? Is that something we can measure? I mean, you can say, sure, I'll take a test, right? I'll give you a test, that'll measure your knowledge. You just took a quiz. Well, knowledge was used to make that quiz, right? So we've got a problem here because we scientists, we like to measure stuff. We like numbers. We can't actually quantify, measure intellect, right? I can't do that. That's not something that I'm able to do, right? If I took my brain out of my skull, that'd be bad news for me, I'd be dead. But if I sliced my brain in half, right? I took my brain and I cut it open. You could see the neurons and the cells and the blood and all the parts of the brain that you learn about in anatomy class. But could you see the knowledge that you've built over your life? Could you see your intellect? No, that's a problem, right? Scientists, we like numbers. We like measuring things. And you can't take a brain and measure the amount of knowledge. Knowledge is not something measurable. Okay, so this is my advice to you as a science student, because I know many of you are going to go on to take further science classes. Try to avoid positivism in your scientific reasoning. And if you take philosophy class, maybe you'll talk about positivism in there. This is a quote. Maybe you'll recognize who it's from. The positivist understanding that is widely held to be the only genuinely scientific one. Anything that is not verifiable or falsifiable, verifiable means confirmed, right? I do an experiment and I confirm it. Or falsifiable means I do an experiment and say, nope, that's wrong, right? Anything that is not verifiable or falsifiable does not belong to the realm of reason. That's the positivist view. In other words, you can't measure it, it's not gonna have a role in your life or in your enterprise as a career. So this is from a man named Joseph Ratzinger. He's lectured in Retzenberg in 2006. Anyone know him by another name? If you don't, that's okay. Here's another quote to think about. Again, the brain, right? Can I verify that there's knowledge in there with a quantifiable test? Well, sure, I could take a test, but knowledge was used to take it. If I look at the brain itself, I can't see the knowledge, right? Truth is more than knowledge, right? Truth means more than knowledge. We're trying to get into some philosophy here too, I guess. And again, this was the same person addressed to educators in 2008. So my advice to you as a science student, we as scientists rely on lots of assumptions that we can't measure, right? We can't measure the fact that we have knowledge at all. You can't measure your intellect other than a test, but again, intellect was used to make that test. So from me, my advice to you as you go forward is try to avoid positivism as much as you can, right? Don't fall into that trap of, if I can't measure it, then it must not exist, or if I can't measure it, it must not be important, or if I can't measure it, it must not have value. That's just my advice. Take it or leave it. I always like to try to bring in some of the philosophy of thought and rational thinking into some science classes, especially in the intro level, because I know many of you are going to go on to take more science classes, hopefully chemistry classes, but more science classes nonetheless. Any thoughts? Any thoughts? All right, so what we're doing today, I'm going to put this in the view mode, the share mode, share screen, so that my students who are watching this online can see it. We're going to do some enrichments here in class. I'm going to pause the recording, give you time to work on this. I'm going to give you a handout with this on it. You have to write it down. So if you're watching this online as an online student, pause the recording, try these problems on your own. Use your periodic table. You can't do this without a periodic table, or diagonal rule if you prefer the diagonal rule, either one. Write the full and then give me the condensed, right? I want you to get an appreciation for the condensed, right? Because writing the full gives you a great appreciation for the condensed. And sometimes maybe the full and the condensed are pretty much the same. So we want to compare those two for these elements. And then there are the rest of them. And then here's some more problems. So pause the recording, try it out on your own, and then resume when you're ready. And then here are some more to try. For each orbital, state the values of n and L. Pause the video, try it for yourself, resume when you're ready. And then here are the last ones. I think there's, yeah, that's it. So n equals 3 down to n equals 5, and there's the last one. If you are doing this as an online student, you can download a PDF from the course website, so you don't have to deal with pausing the video. You can download this from the course website as well. So I'm going to pause the video, give everyone time to work on this, and then we'll go over it. All right, let's go over these enrichment problems. So in the beginning, we are writing both full and condensed. And so the idea here is we want to see the relationship between full and condensed, because some elements, like hydrogen, there is no condensed, right? And for helium, it would just be itself. And for lithium, it would be helium plus one left over, right? So sometimes the condensed doesn't save you a lot of time. So let's do beryllium. The full would be 1s2, 2s2, 2p2. Oh, wait, yeah, 1s2, 2s2. We're not doing carbon. It's just 1s2, 2s2. Do we agree? Beryllium, 1s2, 2s2. To do that in condensed, that would be helium, 2s2. See, that doesn't really save you a lot of writing, right? Because you're either writing 1s2, 2s2, or you're writing helium, 2s2. Either way, it's not really the biggest of savings. Let's do magnesium. Magnesium full would be 1s2, 2s2, 2p6, 3s2, right? That gets me to magnesium. If we're doing it in condensed, that would be neon, 3s2. Do we agree on magnesium's electron configuration? Right, because all of this is taken by neon. So all we have to deal with are the leftovers. For potassium, that's 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. We'll get a big savings to do it in condensed notation for potassium, right? Because for potassium, all we have to do is argon, and then 4s1, right? Because all of this goes away when we write argon, and then we just have the leftovers. I'd tell you a good chemistry joke, but all the good ones are gone. All right, molybdenum is number 42, so writing it out is going to take some time. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. I'm going to write here 5s2 4d 1 2 3 4. All right, that's a long one to write out, but in shortcut notation it's great. Go up into the end, so that gives me krypton, and then I have to deal with my leftovers. 5s2 4d 4. Do we agree on molybdenum? All right, for fluorine, that's number 9, so that one's pretty short. 1s2 2s2 2p 1 2 3 4 5. And if we're doing it in shortcut notation, that would be helium, and then 2s2 2p5. So in terms of what you have to write, it doesn't really save you much to do it in shorthand here, right? Because helium only takes the place of 1s2. So when n equals 2, it's not really saving you much to write in shorthand. When n equals 5, it's saving you a lot to write in shorthand. Okay, chlorine's number 17. So 1s2, 2s2, 2p6, 3s2, 3p, 1 2 3 4 5. Right? Chlorine's directly under fluorine. So now for shorthand, we say neon, and then we have to deal with the leftovers. So 3s2, 3p5. All right, for selenium, selenium's what number? 34, right? It's right there. So it's in n equals 4. So we've got some writing to do. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 1 2 3 4. Do we agree for selenium? We'll get some savings writing this one in shortcut. We go argon, and then we just deal with the leftovers, 4s2, 3d10, 4p4. Because argon takes the place of all of that. Neon, longhand, neon's number 10, 1s2, 2s2, 2p6. Neon's not going to get us any savings writing it shortcut, right? Because neon, the only thing that we're going to get to take away is 1s2. So helium, 2s2, 2p6. Copper, what's special about copper? There's something special about copper. It's one of the, there are 4 that are anomalies, right? Which ones are they? Chromium, molybdenum, copper, and silver, right? So copper is one of the anomalies. To write it out longhand, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Right? Copper is one of the anomalies. It's more stable from a quantum mechanical standpoint to have that D block completely filled. Yes?
For the MO one, isn't that one that we have to be careful of too?
No, because molybdenum is 2 away. Oh wait, molybdenum's down here. You're right. 5s1, 45. You're right. I just totally blanked out on that. You're right. Molybdenum is an anomaly for that same reason, right? It's more stable quantum mechanically to have the D block fully filled. I just was zooming along and wasn't even thinking about my anomalies. 5s1, 45. So minus 1/2, Dr. Bruck. Right? It's a sad looking sad face. If you did that, you'd lose half a point, right? I'm just zooming along here, wasn't even thinking. Yes. Chromium, molybdenum, copper, and silver. And it does technically apply to these 2 as well, but we have to go through the F block, which is not something I'd make you do. So if that was what you did and you just forgot about that anomaly, like I did just now, right, you'd only lose half a point. Okay, so to do this in shortcut notation, that would be copper, go up a row to the end, argon, 4s1, 3d, 10. And yttrium is in n equals 5, so there's some writing to do. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3p10, 4p6, 5s2, yttrium 4e1. That's a lot. To do that in shortcut though, go up a row into the end, that gives me krypton 4d1. All of that gets taken care of by, oops, forgot the 5s2. 5s2, 4d1. All of this gets taken care of by krypton, and I just deal with my leftovers. Now remember, if you're doing this via diagonal rule, that's fine, right? Just sketch out oops. All right, this is S2, 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 6, P6, 6, P6, 6, 6, D10, 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 F14, F14. Okay, so just a reminder that if you're doing it via diagonal rule, you'd have to figure out where your element leaves off, right? And then start there. So for instance, if you're doing fluorine, helium leaves off here at 10. Helium leaves off here at 2s2, 1s2. You would start here. If we're doing neon, neon leaves off at 10. You would start here, right? So just figure out where your element ends on the diagonal rule and start from there. That's just the one little glitch with the diagonal rule that you don't have to deal with in the periodic table. But either way, you'll get the same answer. Any questions on the first ones? Okay. So on a test, if I say give me the full, obviously give me the full. If I say give me the condensed, give me the condensed. And if I don't specify, you can give me either one. Okay, so if I say just write the electron configuration and I don't give you any sort of restrictions, then you can write whichever one makes you happy. But if I specify, do it for X, Y, Z elements using condensed notation, then you would obviously use condensed notation. All right, review off to the side. So the last electron added to yttrium, that's 4d1, that's that electron. So for a 4d orbital, n equals 4, and let's make our cheat sheet, 0, 1, 2, 3, S, P, D, F. And L equals what? For a d orbital, L would be 2. Man, my markers are getting low. Okay, let's sketch this orbital. We're sketching a d orbital. So a d, right, you could draw the clover leaf. My lobes are kind of off. They should all be the same. You could have also drawn it like this. Just don't forget the hula hoop, right? I'd accept either one. Okay, what are the values of N and L for the last electron added to potassium? Potassium would be right there, so that's 4s1, right? So N equals 4 and L equals what? 0. And so what would that orbital look like? What shape would it be? Just a circle with a radius of 4. Do your best. It's a pretty sad circle. Questions on these? All right. Let's scroll down to the back. For each orbital, state the values of n and l. Okay, for a 2D, n equals 2, and l equals what? Is that allowed? No, that's forbidden. Or you could write forbidden, you could write does not exist. And then if you tell me that, what's the reason? If you tell me something's forbidden or something doesn't exist, why does it not exist? What's the reason? Right, n cannot equal L. Good. Okay, so that does not exist. All right, 1s. N equals 1 and L equals, is that an allowed combination? Yes, that's allowed. Okay, n equals 2 and L equals 1. Is that allowed? Yes. N equals 6 and L equals, is that allowed? Yes. N equals 5 and L equals 2. Is that allowed? Yes, that's allowed. Watch out for those sneaky ones that I might throw on there, because I like to see if you're watching. So if you saw something like this on a test, you would just write does not exist, right? You wouldn't write values of n and l, because if you wrote values of n and l, I would think that you knew that you would think that it exists, right? So if you saw something like that, you'd say a 2D doesn't exist. Even you can prove it to yourself by the periodic table too. Look, when n equals 2, does it go through the D block at all? Right? When n equals 2, your only options are S and P. So you can always verify from the periodic table. Okay. N equals 3 and L equals 1. Is that an allowed combination? Yes. So the name of that is 3 what? P, right? 3P is on the periodic table. Oh. Yeah, 3P would be right there. Sorry. I was thinking 3D for a second. Wait, 3D doesn't exist. 3P doesn't exist. Okay, so a P orbital has what shape? You can draw it a couple different ways. It could look like the number 8, right? It could look like the infinity, where you can draw it kind of diagonally. Whatever makes you happy. Just try to make your lobes as close to the same as possible. You don't have to get obsessive about it, but make them as close to the same as possible. N equals 0 and L equals 2. What does that produce? Nothing, right? Does not exist. Why? All right, n cannot equal 0. Good. N equals 1 and L equals 0. Is that allowed? Yes, L can be 0, n cannot. What's the name of this? 1s. What would that look like? Middle circle, right? And n equals 5 and L equals 2. Is that allowed? Yes, what's the name of that? 5D, right. So that would look like, right, you could draw the clover leaf, again, try to make it as close to the same as possible. Or you could draw the version of a D that looks like that. Or if you drew your lobes in between the axes, that works too. But there are a lot of variations on the D orbital. And in intro chem, we don't get obsessive about which variation we're looking at. Is that the last one? Oh, we still have one more. zoom in so I don't have to stoop down so low. N equals 2 and L equals 3. Is that an allowed combination? No, it does not exist. Why? All right. Good. Because N cannot, L cannot be greater than N, right? The max value of L is N minus 1. So if your value of L is greater than your value of N, it doesn't exist. Nothing should go up. Good, 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 good. Questions on this? Questions on this? All right, so I believe you have a quantum model quiz coming up. Yes, you do. So this is the stuff that will be on the quantum model quiz, okay? Everything from this is fair game. I'm also going to scan my answers and post it on the course website. So if you want to go back and look at this without watching the whole video, you can look at the PDF. It'll be posted on the website. That way, if you don't want to go watch the video, just see something to review something, you've got that as a PDF as well. All right, if there are no questions, that's where we're going to stop.